Over to you, Bettina. Thanks a
So,
lot in advance for your talk. We're very much looking forward to the interesting topic of today's NDT4Industry talk.
yes. So thank you for the introduction and welcome to my talk. I hope you can all hear me. And I want to speak a bit about coherent imaging and recovery of the information which are more or less encoded in these type of images. And you have already heard I'm the head of OCT and digital imaging technology at RECENT. And so also comes a bit the topic about which I want to speak, and it's on one hand connected with optical coherence tomography, OCT. And I want to give some words as introduction at the beginning. I want to come to speckles and a bit to signal processing and image processing, what you can do with these speckles, why they can be also useful. And then finally, I show you some examples about extracting these images and the information from it. So maybe are you avoid this? OCT comes from the field of medical application, and I think you have maybe known that this development started about 10-20 years ago in ophthalmology. What you get by this technique is a cross-sectional map, a reflectivity map, and it works mostly in the near infrared as a non-destructive and conductless measurement. And in such a way, it is also over the last years transposed from medical applications, also in the field of material science, in the field of non-destructive testing, to get information about the quality and about diagnostic of some defects and some faults. The materials which we investigate are more or less transparent materials, semi-transparent materials. They are scattering often. They can have a layered structure. And so the information we want to get is the structural composition, are the artifacts, or are also functional information about elasticity and birefringence, for instance. OCT from comparison with other techniques, partly also with other techniques we have available at our affiliation RECENT, is an imaging technique which is in the range of about 1 millimeter penetration depth, but with a resolution of some few micrometers. It stands between confocal microscopy and terahertz imaging, and also to ultrasound. Let me say some words about only some schematics at the beginning. You know, maybe if it's a basis of interferometry given here, and it is first realized in time domain. Meanwhile, we do OCT in spectral domain and web source OCT realization. So that is more or less in realization of this technique in Fourier domain, where we measure the spectrally resolved interference. And we can have it as in raster scanning methods, and we can also realize it with an area illumination as in full field OCT or full field OCM. And in such a way, we get this information. And what is mainly measured in OCT is the reflection, the strength of reflection and the runtime, how long it takes that the signal, that this reflection comes back. That must be done in an interferometric way, as we have the speed of light, and partly we have also scattering. Additionally, we have also refraction and absorption within the material, but the typical image for OCT is what you can see here in the right. we can see interfaces, and we can see also strong scattering regions. And we can see also, for instance, some small inclusions here. And why we get such a type of image? Yeah, OCT belongs to these imaging modalities, which are coherent imaging techniques. Beyond what we get of reflection, here some examples for typically images which are measuring reflected strengths. We get also some contributions which are coming not from direct reflections, they are coming from scattering and from multiple scattering. And you can see it also here nicely, maybe in these upper left images, that is more or less directly reflecting components. These are 3D printed components which have the same material as matrix, but they have different pigments, and so they are different in their scattering behavior. And that is in more transparent specimen, and you can see the defects nicely. Here in the right side, we have two intermediate, I would say, quantities where you can slightly see the defects still and have a moderate scattering. And here that is an example where we surely have as well these defects, but they are hidden under the scattering, under the scattering effects. So these, let me say, giving a bit in motivation why to deal with scattering, why to deal with speckles and so on. And that brings me a bit more to the theoretical part to discuss about coherence, which is more or less the background, the reasoning why we can also get these effects here. And coherence is not only restricted to optics, we have it also in other technical fields, in fluid dynamics, where we speak from coherent flow patterns, or we find it also in context of financial economy, where we say coherent markets, but more or less coherence describes correlations. And in optics, it is more or less the coherence features of waves, and they can be fully coherent, they can be partly coherent, or somewhere also incoherent. And that is also a second, let me say, statement. If a coherence is long or short, that is also a question of scale and must be considered in the context of the application. And what we still have additional is that we have coherence related in time, that is more or less the phase stability of a wave in time. That depends from the spectral width of the light source. So if it's very narrow, then we have a very long temporal coherence. If we have rather broadband sources, then it comes to low coherence. But that in principle we can also define for thermal sources, but then this expression goes very down, below 1 micrometer. And additional to the temporal coherence, we have also the spatial coherence, which is also dependent from the wavelengths and inversely from the divergence angle of the source. And these both quantities give us the freedom to be designed for the application and can be exploited. So only here as a short overview, I think you maybe know it, these different light sources which we can discuss. Laser with very high temporal coherence and also high spatial coherence. And on the other side of the spectrum, we have thermal light sources with very low temporal coherence and also very low spatial coherence. And between we have these sources which we often use with where we say low, moderate coherence, supercontinuum sources or the femtosecond pulse lasers, LED or SLDs. That can also depend if they are propagating or emitting in the free space, or if they are coupled in a single mode fiber. By this, we can steer the coherence. And what is then more or less if we have high coherent sources, like say lasers and so on? I think you often have observed yourselves if you send some laser light to some rough surface, then you get speckles. These are more or less random fluctuations and describe random interferences. And depending on from the coherent degree, they can be fully modulated or partly modulated, but more or less you get such a patch-like pattern as you have here. And they can be directly measured, or they can be projected by lens system to some imaging planes, and we discriminate between objective and subjective speckles, and you can also be tuned a bit in the size. And yeah, is this only a random pattern or give it also some information behind? So these speckles, on one hand, often they are considered as noise. One tries to smooth it out by different averaging techniques, by measuring with slightly jittering configurations, or measuring slightly under slightly different angles. And so this random pattern is more or less smoothing out. But other techniques are also using these speckles. One of maybe is electronic speckle interferometry, and also coherent imaging, speckle coherent imaging, and try to extract the hidden information which is behind this pattern. And let me give you a bit here in theoretical scheme how one could produce such speckled patterns. We have some coherent source, and collimated laser, for instance, with relatively high coherent in time. We have some defined object. We have a diffuser, which can also be rotatable to get more redundant information, and we have a lens system which produces now, after this diffuser, the image to a camera. And if you see here for these simulated data, we had, let me say, such a pattern, and what you would observe at the camera is such a specular image, a bit enhanced in contrast in the middle. And what you can do to extract the information now is one way, which is also called phase retrieval. What is phase retrieval in general? You know, you can only measure intensity, and more or less if you take a camera directly, as here is sketched, but you lose the phase information. And slightly connected also to this approach is that you have a pattern. You build the autocorrelation, but you want to recalculate what is your original object. And the approach is here now, you build the autocorrelation of this random, like noise, like speckle pattern. You have the autocorrelation, which is more or less slightly modulated Gaussian, more or less similar to some delta function. And by phase retrieval techniques, you try to reconstruct this original image. So the mathematics which is behind is you build an autocorrelation of your measured image, that is here in this equation. And the image is formed by the convolution of the object original object with the point spread function. So here the speckle pattern is more or less gives the point spread function. And if you assume that the speckle pattern behaves a bit like white noise, then you have the correlation, the autocorrelation of the object and the autocorrelation of the speckle pattern. And since convolution and correlation are interchangeable, you can separate it in such a way. You have a correlation between the object and you have a correlation between your point spread function, and you know autocorrelation of an image which is more or less like white noise gives a delta function, and then you multiply more or less your object with a delta function, and that is more or less the original object. So the mathematics which is behind that, also it is destroyed or modulated by the speckle pattern, the information content is the same as if you would consider your original object. And so you can also, by some iterative phase retrieval methods, reconstruct your original object. And that is what more or less here is resulting, taking this autocorrelation function from the beginning and reconstructing by iterative approaches. You see what can happen in such reconstruction. You see it not only one time, so the solution is not unique. You get also the mirrored, more or less, object configuration. But in principle, it is possible to reconstruct also from speckle-like images this hidden information which is encoded in such a pattern backwards. Other way, that was a phase retrieval approach, which I have illustrated here. Other way, which is also a bit more connected to OCT imaging, is to exploit speckle statistics. So to consider probability density function, to use moments, to consider also random texture as a third method. And I will illustrate with the next 3-4 slides a bit these issues. So the moments is more or less you consider, you take an assumption about the probability function and calculate the first moment or the second moment, with is more or less correlating with the variance. And interesting, and that I want to mention here, is the first moment is a shift in the mean that you can see nicely with the eye. The eye is also sensitive to see a change in variance that is also feasible. These are the first and the second statistical moment of a speckle pattern. But higher moments, like the third moment, which is also describing the skewness in histogram, you cannot see by the eye. But by mathematical methods, it is extractable that the upper region and the lower region in this speckle pattern is differing. And that can be analyzed by this moment analysis. Other way is to use entropy. And in OCT, we have also these speckles more or less connected with scattering materials. Okay, here a typical OCT image, and you can see different scattering regions and how we can now discriminate. We could apply histograms, so for instance. We could apply autocorrelation functions, or we could apply local entropy methods. So these are all versions of analyzing statistical speckle patterns. It works sometimes better, sometimes not so good. Another way, which is coming nowadays more and more, is to learn such speckle patterns, to learn it, for instance, for segmentation. And here a tool which is not from us, it's from University of Heidelberg, but it works very nicely also for OCT images. And one can train it interactively by, let me say, the expertise which one has in such type of images. And one marks some regions according to with the colors as the labels, and then it is automatically segmented. And one can improve it stepwise to, that the user is pleased with the final result. That is also a way when behind are features which I have described you before in statistics, in texture analysis. One can do it in different scales, and that results that we can analyze these speckles and use them with their different features, with their different statistics and texture to segment them. Other question is, if you would have such an image, you would also maybe not see very much with your eye. But what is behind is a time series. And it's a tensile test where a scattering polymer has been stretched in one direction. In one direction it was fixed, in one direction it was stretched. And one can do a speckle statistic analysis over time, and for instance would get such an variance image in regions where you have high alterations of this speckle statistics, speckle moments in time, in regions where it is lower, and some regions where you have only noise. I hope it, I'm not sure if it should be a movie. Okay, but you see the result. It's in principle a time series, and it is running over time, and you can do this statistical analysis. You can also do correlation images. Also, that is a way to, here you can see it now in this upper movie. In the gray scale images, in the B scans, you see maybe a bit with good eyes, a bit that we have in slight movement of the speckle patterns. And in the pseudo-colored, it is analyzed by statistical moments, and you can discriminate these regions where you have a high flowing of the speckle patterns, the white region where it's more static, and the brownish region is where you can have no deep information due to noise. And finally, here we can also use to do it in a quantitative way to say how much is the similarity between images, between image patches. To one of these sizes is the so-called structural similarity index measure, which is a bit accepted to the human perception and give a measure for similarities of speckle patterns also here in this context between subsequent frames. So then I want to illustrate you to say that speckles, although it is often considered as noise, give some very valuable information as well. It can also cope from a different side. We can not only use mathematics, we can also improve optical settings. We can go to higher wavelengths. Then we modify also more to mid-infrared range, from typically near-infrared range to mid-infrared range. Also that influences speckle patterns, that influences the information we can see or which is hidden in the very left image, which is taken with an OCT at 1.3 image, or it's in simulation here. You see no structure below, and it's a prediction in these Monte Carlo simulations that for wavelengths higher than 3 micrometer, also the scattering is decreased, and then hidden structure becoming visible from a measuring point of view. That we have tested recently in our mid-infrared OCT, where we can see also in ceramics hidden structure, where we can get porosity mappings. And also here you can see the comparison at 1.3, it's almost not visible. 1.7, it's become slightly visible in such a way. And that is a way also to compress, to hinder a bit the scattering, to go to higher wavelength ranges. also what is encoded as well is information about polarization and optical anisotropes, which you can also not see directly in a conventional OCT. Here in the upper image, you see nothing, that there is some internal structure. In the lower image, you can see some flow pattern, and that is obtained by a so-called polarization-sensitive OCT, which measure it according to 2 polarization channels and can give information about birefringence. Here, for instance, you see here also the conventional image and the birefringent image. I will see. I have a bit more problems with the videos. They are not running, or now they are running. And you can see in the upper images more or less no information, but in a polarization-sensitive OCT, information is encoded in the speckle pattern, producing these fringe-like speckle pattern here. And these fringes can be analyzed. That is maybe another topic one can speak how to analyze these fringes and extract the information which is here. In context of polymers, these are often information about stress and strain states. And yeah, one can also do some analysis coming from such a polarization-sensitive scan to finally information about the stress. So more or less the density of these fringes encode the strength of the stress or can encode the strength of stress in such type of polymer images. So finally coming to the end, I think I must come to the end. Here are some applications from polarization-sensitive imaging OCT modalities, where you can see also here is encoded information. And very finally, that brings us back to some application field, which I only want to show you, is the analysis of gemstones, where you can also have a lot of features, scattering, and more transparent features. And with this image, I want to finish my talk. If you want to read a bit about our last publication in ceramic imaging by means of mid-infrared OCT, you find here some literature. Also another application which we have currently published is in-mold OCT. And today I'm speaking not from RECENT, I'm outside at Jena, and that gives me also the opportunity to make a hint on this guideline, which are we working on. And these are guidelines about OCT images, where all these features are also a bit described in more detail. And if you are interested, you can also order these guidelines. So far a bit advertisement. You also have my contact data, and yeah, I'm interested in your question. I thank you for your attention, and well.
Thank you very much, Bettina, for this talk.